Okay, hello everyone. Good evening. Welcome to join Space Observations and Sustainability course today. Today's lecturer is Professor Shou-Hao Jiang, and he's from Center for Space and Remote Sensing Research, National Central University. And his research interests are spatial modeling, physical geography, hydrological process, and landslide modeling. Okay, Professor Jiang, can you hear me?
Oh, yes.
Okay, please.
Okay, I'm today's lecturer. I'm Shou-Hao Jiang. I can simply call me Gilbert. I'm now serving as an associate professor in the Center for Space and Remote Sensing Research, as mentioned by our assistant. Okay, today's topic is about the nature disaster and focusing on debris flow and landslide. And I understand that for today's lecture, we are going to focus on study case and about the debris flow and landslide studies. And today I provide the following outlines for you to, probably got offline and don't know why. And anyway, I'll continue. Today's lectures will be a 2-hour lecture, and I divided today's lecture into 4 sessions. The first part is about the overview of landslide and debris flow hazard, giving a very brief introduction and the concept and definition of what are landslides and debris flow and their caused hazard. And the second section is about the tracking mechanism of landslide and debris flow. So for this section, I will talk more about the theory part, focusing on the triggering mechanism of this natural disaster behavior. And the section 3 is practically how we use techniques or models to assess the landslide susceptibility for hazard prevention purposes. And section 4 will be a case study from my previous study talking about an integration method for modeling landslide and debris flow. And the last session is kind of open questions, and I'm trying to give you the challenge and future work dealing with this topic, in my opinion. And let's move to the section 1, which is about the overview of landslide and debris flow hazards. And in the beginning, I would like to share this video, which is about the event in 2013. And this is a raining day. I can see the raindrop hit the window. And you can see this is driving across a flooded area. And suddenly you see something happened. Before I introduce what is a landslide, I believe this video is more easier for you to understand the impact of landslide and how it causes hazards. Unfortunately, for this event, no one get hurt. But I don't think this because the landslide is not dangerous just because the guy is lucky. And let's see a next event, which happened a few days ago in Taiwan. I think this guy react very rapidly, just driving back his car. And luckily, you can see a landslide just occurred in front of the car. So These two videos remind us how a landslide can be dangerous. And what is a landslide? Landslide, by definition, is a geological phenomenon which includes a wide range of ground movements. A landslide is the movement of a mass of rocks, debris, or earth down a slope under the influence of gravity. And here I show you figures indicating a very typical form of landslide. You have the crown cracks. There's a crown part, and you have the failure side, and you have the transverse cracks, and also those so-called failure materials can be moved down to downslope area by gravity. And this is a very famous event and taken by the USGS. So you can see a significant scar here, and the failure materials move downslope, and those failure materials can further affect the residents, those houses, and maybe people. And in terms of types of landslide, we can have several categories like flow, topple, slump, and slide, creep, and fall. And what are they? We can use this table to characterize the type of landslide by the type of movement and also the type of material. And you can see those categories mentioned in previous slides as listed here, and associate different engineering soils, including bedrock and fine materials and coarse material. You can have different types of slides, like rock fall or rock top, rock slide, and so on, and earth flow, earth topple, earth slump, earth black slide, earth slide, and spread, and earth fall, and so on. And for coarse materials, you can see the category debris flow are listed here. So you probably can understand that when we talk about landslide and debris flow, in many cases, a debris flow is also a kind of a company with landslide. And this is a good example that you can see debris flow occurred in this flood plain. And by definition, debris flow is a geological phenomenon in which water-laden masses of soil and fragmented rock rush down mountainous sides, funnel into stream channels, and enter objects in their paths, and form thick, muddy deposits on valley floors. And however, you should know that the major materials of debris flow mostly were coming from landslides. This is a video showing a debris flow attacked a mountainous village in Japan. And debris flows are fast-moving landslides that are particularly dangerous to life and properties because they move quickly and destroy objects in their paths, and often strike without warning because of the movement is very quick. Normally, people or government have limited time to respond to this kind of disaster. And specifically, the hazards caused by landslides and debris flows can be like destruction of the road in mountainous area like this, and the failure materials attacking the downslope and valley, and also even in the gentle slope, you still have a chance to have landslides in like and then attack and destroy important road. For example, the highway. This has happened in Taiwan a few years ago, and also the villages. And in addition, for watershed management, landslides is another issue that cause materials and sediments into channel systems and probably eventually enter the reservoir. For example, this is in 2004 in Taiwan. This is a very important reservoir in northern Taiwan. And after the landslide and Davisville event, you can see a significant increase of the turbidity of the water. Therefore, will significantly impede the water supply of the down catchment area. Okay, now I think we probably have a better idea about landslide and debris flow and knowing what are them. And the second part is about the session deal with the focusing on the triggering mechanism of landslide. And what are the landslide triggering factors? The landslide triggering factors include external, internal, and human factors. The primary external factors that can trigger a landslide include wearing of the rock strata and increased pore water pressure, such as the infiltration of the rainwater or the rise of groundwater surface, and increased loading by, for example, rainfall, accumulated snow, or forest vegetation. And the supporting forces of toll have been removed by, for example, weathering, erosion, early landslide, or faulting, and collapse of underlying stratus, and an increase in lateral pressure such as rock fissure, freezing water, expansion of clay materials, and so on. And also, landslide can be triggered by, of course, landslide and vibrations, and terrestrial rainfalls, including like storm or typhoon. For other factors, such as side subsidence result from like limestone cave or human pumping. Those are external factors. And how about the internal factors? The internal factors of landslide formation are related to the soil and rock materials. And basically, we are talking about their strength and resistance. So the factors are soft and weak rock properties or rock stratus with multiple joints or shear fracture zone, and geological structure. Of course, the topology, or we can call it topographic. For example, the slope, the aspect, and the curvature, which is the shape of the slope, and also the vegetation. Normally, the vegetation, for example, the tree roots, can provide a certain of surcharge to increase the resistance of the surface slope, preventing failure of the materials over the slopes. And for human factors, for example, remove a portion of slope toe, the slope can become steeper, therefore, and build houses on the slope, which is increasing the slope loading, and pipe out human-made waste, which increase the driving forces of materials on the slope. And also, an inappropriately selected site can be also affect the slope stability and trigger a landslide. For example, or construct a road on the top or below the slope. And when we talk about the trigger mechanism of the rainfall-induced landslides, okay, before that, I have to mention that for today's lectures, when we focus on the trigger mechanism of landslides, I would like to divide into two parts. The rainfall or water triggered, and the other one is earthquake triggered, because those two are so-called major factors triggering landslides of the natural disasters. And in here, I would like to introduce the trigger mechanics of rainfall-induced landslides. Firstly, And later I will talk about the triggering mechanism of earthquake-induced landslide. And the mechanism is that a soil moisture water content, or we call it soil saturation, of a slope is a primary cause of landslides. So you can see this explains the entire process. During the rainfall event, you have precipitation, and those rainwater can infiltrate into the subsurface system, for example, the soil or the bedrock. And then the infiltrated water may accumulate it over this bedrock surface. I would say over this between the bedrock and the soil layer, and forming a saturated layer and increasing the so-called purchased water table like this. And this water table, or this amount of water, will significantly reduce the resistance of the surface material, then causing landslides. Therefore, this effect can occur by intense rainfall, snow melt, and increase of the water level. And why the soil moisture or the pore pressures can be very important in reducing the shear strength or the strength of the surface material. We can look at these experiment functions here. This line is so-called value in envelope, and this figure is formed by the shear stress and normal stress. And the stress can be the equals the cohesion plus the normal stress times the tangent of the friction, internal friction angle. So when we talk about the stress or the resistance or surface of the soil or rock, we are looking at the cohesion and the internal friction angle part more importantly. And if you look at the experiment shown here, this line showing the cohesion is decreasing when the saturation is increasing. And also you can see the similar pattern, although it's relatively insignificant for the internal friction angle. So by the experimental result, we understand that when the soil saturation or the soil water content or soil water pore pressure is higher, then we have lower resistance of the surface material. Therefore, we have landslide. Okay, this is a major mechanisms of the rainfall-induced landslides, all because of the water, which is the major factors. Of course, we have other factors like slope and the aspect and the property of the geological things, but they are categorized as internal factors. And the triggering mechanism of rainfall-induced landslides normally will trigger landslides over a slope which is more close to channel. You can see the two figures are taken in, this is in Japan, I believe, and this is in the southern Taiwan. And if you look at the pattern of landslides, you can see normally those landslide scars are close to the channel, river channels or valleys. That means those valleys or channel valleys can accumulate water quickly, more rapidly than other slopes. Therefore, it has a higher capability of accumulating water. Therefore, reduce the materials, the resistance of the slope materials. So by looking at the shape of the pattern of landslide, we probably can tell the triggering mechanism of the landslide. And then I would like to introduce some study case in Taiwan. And for studying the rainfall induced in Taiwan, normally we are looking at the typhoon event. we consider that typhoon is a major trigger of landslides in Taiwan. In general, 4 to 5 typhoons strike Taiwan every year. And the rainfall data statistics summarized between 1916 to 2013, and 84% of maximum annual rainfall events were induced by typhoons. And more than 90% of the rainfall intensity, which is greater than 200 millimeters per day, were induced by typhoons. And 80% to 70% to 80% of annual total rainfall is contributed by typhoons. Therefore, you can quickly understand how typhoon is important in providing rainfall water, and therefore also not only amount of the water, but also the intensity of the water. Therefore, we may the landslide can be a significant control by the typhoon event in Taiwan. And some study from my previous study, we have evidence saying that the rainfall controls, firstly, the spatial distribution, or we can say the location of landslides, and also the magnitude of landslides. Let's see some example. And when in this study, we want to correlate the spatial distribution of landslide and the spatial distribution of rainfall. And the easiest way to understand the distribution of the rainfall is to look at the data from rain station. However, if we are going to study rainfall distribution for a watershed or for a catchment, the available rain gauge stations, station data can be varied among the different study cases. Sometimes we can have 19 rain gauge stations over an area of 750 kilometers square. And however, sometimes for this case, we only have 7 rain stations over a study area greater than 5,000 kilometers square. So the availability of rain station really affect the study to know the distribution of rainfall. And the other issue is that normally we will place rain station in a terrain which probably can be relatively flat, which it can be suitable for construction of rain station. However, those locations cannot be can have a significant discrepancy between landslide location and this rain station. Therefore, this is we may argue that the representative of the rainfall data over rain stations those data can be a good representative for the rainfall over landslide areas. This is very questionable. So to overcome this issue, we use the rainfall estimation methods, which is using radar data provided by QP-SUM, which stands for quantitative precipitation estimation and segregation using multiple sensors. So the functionality of the QP-SUM is very easy to understand. Firstly, we have the radar stations around the Taiwan island, and those radar stations will collect the reflectivity. And by using some mathematical methods, we can convert the radar reflectivity into a rainfall map. And by doing some adjustment or correction, we can obtain the distribution of the rainfall. This is not directly from the rain station, but from the radar, which is a type of remote sensing technique. And by doing so, we have higher evidence to have better quality of the rainfall distribution information. And by having this kind of rainfall data, we have a chance to study the spatial correlation between the landslide location and the rainfall distribution. And this study case is focused on a typhoon event, Typhoon 80 in 2004, and the study area is the Shimen watershed in northern Taiwan. And you can see the landslide number is about 653 induced in this event, in this typhoon event. And you can see we can generate the rainfall distribution, including the 3-hour rainfall intensity and the total rainfall and rainfall duration. These three are rainfall variables to correlate the landslide distribution here. And visually, we can understand that it shows good corresponds between the landslide and the rainfall pattern. And we also use a statistical model, which is the logistic regressions, to understand the significance using a statistical model. So this map shows the probability of landslide occurrence controlled by two variables, rainfall intensity and rainfall durations. And from these studies, we understand that when the rainfall intensity is higher and the rainfall duration is longer, we have higher chance to have landslides. Therefore, apparently, rainfall controls the distribution of landslides. However, this rainfall also control the magnitude of landslide, saying the size of the landslide or the area of landslides. In recent research published in 2020, me and my colleagues have this study results. These results focus on the typhoon event in 2009, which is Typhoon Morakot, and showing the distribution of the rainfall in A and the distribution of landslides in B, and also give you the idea of bigger landslides. The landslide size, and you can see these two maps corresponding, I would say, well, saying when you have higher precipitation, then you probably have greater or bigger landslides. Therefore, we can easily conclude that from previous study and those are reviewed evidence, we understand that easily rainfall controls the distribution of landslide and also the magnitude of landslides. And then let's talk about the trigger mechanism of earthquake-induced landslides. And earthquakes and volcanoes contribute significantly to the landslide hazards. And earthquakes create stress that make weak slope fail. And earthquake of magnitude 4.0 and greater have been known to trigger landslides. Volcanic eruptions produce loose ash deposit, heavy rain, and debris flow. And this is the study case in Taiwan, which is focusing on the major earthquake happened in 1999, which is Chi-Kuei earthquake. And its magnitude, I believe, is about 7, greater than 7. And here is the earthquake's epicenter. And after and during and after this earthquake, this is the fault line. The thrust fault line has been uplifted to 9-meter maximum, and the mountainous area, you can see a lot of landslide has been triggered during this earthquake event. And if we want to look at the mechanism of the earthquake and how a slope responds to earthquake's energy, and how it performs as a landslide over mountainous area. These experiments tells us when we shake the mountain by a certain amount of energy, normally the surface value will occur over the top of the slope in advance. So, so this is the photo taken right after the Chih-Kuei earthquake. So you can see different from the rainfall-induced landslides, which normally occurred nearby the streams and valleys. The earthquake trigger landslides normally occupy the top of the mountain. So you can see a lot of bare and removed materials can be found over the mountain top. However, in some environment or geographic characteristic, for example, in Taiwan, we not only have earthquakes, but also typhoons. So it's very difficult to study landslides triggered by rainfall or earthquake alone, because they, in some area, we have to think those factors should combine together. And these studies explain this is the study about the landslide susceptibility analysis focusing on typhoon and earthquake. So you can see the landslide distribution can be very different between a typhoon and earthquake. And you can see, as mentioned previously, the typhoon-induced landslide in generally occupied at the area nearby channels. And on the opposite, the earthquake-induced landslides will more frequently observed over the top of the slope. So, however, this study also shows that how the combined effect of typhoon and earthquake can generate a very different behavior of the position of the landslides. And this figure shows the relative frequency observed in different typhoon events, including the typhoon in 1996 and the Chih-Kuei earthquake in 1999, and followed by a typhoon in 2001 and 2004 and 2005. So if we look at the relative frequency against the landslide locations from 0 to 1, okay, I have to explain the landslide location a little bit. In here, 0 represents the landslide location is more approach to the channel, and the 1 is more approach to the slope top or the ridge lines. So 0 to 1 is kind of standardized position of the landslide along the slope. So you can, for example, the landslide distribution in 1996, before the Chih-Kuei earthquake, you can find that many the white histogram, you can see more landslides were occurred along near the channel. And if we look at the distribution of Chih-Kuei earthquake in 1999, you can see relatively you have more landslides over the top or the upper part of the slope. Okay. However, after Chih-Kuei earthquake, there is another typhoon in 2001. You can see in this dark gray, you can see the pattern of the distribution of the landslide trigger in 2001 has very similar pattern with to the earthquake trigger landslides. And many landslides were found over the upper part of the slope. And however, this phenomenon will change after a couple years later. For example, in 2004, more landslides are moving back to the channel, moving back to the downslope area, which means it's close to the channel stream. And then 2005. So we can summarize the statistics using this graph. And this is the position in 1996. And this is Chih-Kuei earthquake. And you know, the landslide location becomes higher. And then in 2001, similar to the 1999 Chih-Kuei earthquake, and then gradually decrease, meaning the location is moving down. So maybe if the trends can be continuous, then we can probably expect to understand the legacy of the recovery of the earthquake effect on typhoon-triggered landslides. Now, for the study, we haven't any evidence to have any conclusion yet, but this is a good research topics to know, just not the rainfall trigger landslide or earthquake trigger landslide. We have to we are interested in study about the combined effect of earthquake and typhoon. Okay, let's move to the section 3. Okay, before that, I haven't explained that for today's lectures, we have 5 sections, and the section 4 is about the study case, and that will take like half portion of today's lecture, and the section 1 to section 3 is another half. So you can consider the part 1 of today's lectures will cover section 1 to 3, and the second part will cover section 4 and 5. So after we finish the section 3, I'm planning to have 10 minutes break. Okay. And this section is talk about the landslide hazard susceptibility and assessment. And firstly, landslide hazard is the probability by definition of occurrence in a specific period and within a given area of a potentially damaged landslide of a given magnitude. So the definition incorporates the concepts of location, time, and magnitude. Okay, and when we talk about the landslide hazard, the one major factor is really important is that if there's no damage, then there's no hazard. What does that mean? If no one gets any losses for this so-called landslide and debris flow phenomenon, then there is no hazard. For example, if you look at the landslide over a remote mountainous area, no one lives there, and there's a total remoted, and then the landslide or debris flow just a physical or natural phenomenon. However, when this landslide and debris flow phenomenon deal with human losses or damages, then we consider it's a hazard. And this is a very useful diagram showing the entire concept dealing with the GIS-based landslide susceptibility analysis. You can see that this entire analysis framework can be divided into several parts, including the data sources and data management and normative units and data processing and GIS modeling. And finally is the landslide hazard assessment. So for GIS-based data analysis, the The data sources can be from aerial photo and satellite image, or GIS monitoring, field investigation, or laboratory test. And for database are required for the landslide susceptibility analysis, you need to consider the geological map and topographic map, engineering and geological map, and land use map, and digital elevation model, and other semantic map to understand the internal or external factors of landslides. And also landslide inventory, climate data like rainfall data, and laboratory results like a physical text to know the cohesion or internal friction angle of test materials. And you need a general field data and monitoring data. Then you can do the data mining. The data mining is to understand the correlation between the collecting data and the landslide occurrence. And in an easy way, you can base on the expert systems from expert knowledge, or you can also follow the model basis approaches. Then for data processing, it's about to formalize or standardize the format to be used in a GIS environment. And for some topographic input, you can have different units like grid cell terrain units, or slope units, or topographic units, or unique condition units. There are several options can be applied in GIS modeling. And by combining the necessary input and pick up a useful model, then you can perform the GIS model and assess the landslide hazard. That's the entire idea of doing the landslide susceptibility analysis using GIS. And particularly, nowadays, models and methods that are well developed and commonly used for analyzing landslide susceptibility analysis are those four types of models. And the first one is physically based models. And the second one is index-based analysis. And the third one is statistical models. And the last one is so-called machine learning algorithms. And for a physically based model, and for those four types of model, I will give you some examples to understand how the models can be conducted. And I will divide it into two parts. The first one is physically based model and others. Because you can see the differences between those the two main approaches is that for physically based models, the model training is not required. It only depends on the physical parameters you collected, for example, from the field or from the laboratory test. And normally, this kind of model is universal. And for the rest, for other models, the three types of models, the model training is needed, and it normally only applies to the local area. Okay, let's explain those models one by one. The first one is the physically based model, and this mostly or widely used is the so-called critical rainfall model, or we can call it short-step, published by Montgomery and Ditch in 1994. That's a very typical physically based model. And the overall idea is to analyze the stability of the slope using the factor safety of factor, and here, which is the ratio between the resistant force here and the sliding sister here. And also it considers the combined cohesions. Combined cohesion means the cohesions of the vegetation from the root or the materials itself. And also, we also consider the hydrological effect, which is used to estimate soil wetness or soil moisture content using this equation, which we call it a steady state hydrological model. It's very simplified model. And by assuming the factor, the safety of factor equals 1, and also applying the wetness here using this equation, we can modify the critical rainfall model here. So you can see the control of the critical rainfall model, the transmissivity, and the topographic, which is the slope and contributing area, and the bulk density of water and soil, and the interface angle, and the cohesion of the materials. And what's the meaning of the critical rainfall model? A critical rainfall model gives the critical rainfall, which is a threshold indicating the minimal rainfall that would trigger landslide or cause instability of the slope. So by using this model, we can determine the unstable area when the actual rainfall is greater than the calculated critical rainfall. So practically, these studies shows you how this model can be applied. And firstly, you just need to collect all the parameters listed in the equation in previous slide. And if you have the all the parameters as maps, then you can generate the critical rainfall distribution like this. And then for a rainfall event, if you can obtain the rainfall distribution like A, B, C, D, the differences between them is based on different scenario. Then you just do the minus the rainfall minus the critical rainfall, and you can determine the area which are stable or unstable. It says that if the rainfall intensity, I mean the actual rainfall intensity, is lower than the critical rainfall, then it will be classified as stable. Otherwise, if the rainfall intensity is greater or equal than the critical rainfall, we can categorize those areas as unstable, which is very straightforward. And then let's look at the example for other models. And this is a case study in northern Vietnam. And the model test using the 3 different models, and actually 4 different models. The first one is the index-based analysis. We focus on the frequency ratio. And then statistical models, we use logistic regression analysis as example. And for machine learning algorithm, we use a neural network and random forest as examples. So for these study cases, we are going to apply 4 different models. And the study area is here, northern part of Vietnam, close to the border with China and I believe Laos or not sure. Okay, and this is a selected study area as a mountainous area, and the rainfall in 2000. I believe in 2018, and it brings a lot of landslides here. And we can use optical satellite data, which is Sentinel-2, before and after the event, and can delineate the landslide occurrence induced by this rainfall event. Here, I would like to show you a very general workflow of landslide modeling. Especially the landslide model would deal with the training phase. And for landslide inventory, if you have the landslide inventory, then you can prepare the sample data for landslide sample and also non-landslide sample. And those samples will form a database for analysis. And normally we were going to split the samples into two parts by having 30% and 70%. 70% is for model training, and the remaining 30% will be used to test the mapping result, the modeling result. And on the other part is to find out or to conclude the landslide triggering factors. And with the combined data set, then we can place all the triggering factors and the landslide and non-landslide samples in a particular models. For example, the logistic regression model, or random forest or neural network models. Then we're going to generate a landslide probability map. And based on the remaining 30% landslide data, we can check the accuracy of the model performance. This is very general flow work for landslide modeling. In these studies, we consider those factors to be the triggering factors in the model, including the elevation, slope, and aspect, and the curvature, topographic wetness, and distance to strings, distance to roll, distance to fold, and land cover, and land use type, and geological formation, and soil type, and soil depth, and so on. And those are factors that we consider would be relevant to a landslide occurrence will be placed in the following four models: the frequency ratio and logistic regression. Okay, I will not spend a lot of time explaining the theory of those models. I'll just give in a brief explanation. The frequency ratio is determined by estimate the correlation between landslide locations in the past and its factors that affects landslides. So historical data is very important. For logistic regression, it correlates the dependent variables and one or more categorical or numerical dependent variables, like this. This is the dependent variables, and this is the independent variables. For landslide modeling, the dependent variable is binary value. Here, dependent variable is binary value, indicate the presence or absence of landslide, which have the value 0 and 1. So this is suitable for the logistic regression analysis using this logic distribution. And artificial neural network, ANN, is a computational information processing algorithm. And we can prepare multi-layer as the input, or we can consider they are factors of applied environmental factors, and output layer, which are the yes or no, or probability of landslide occurrence. And between them, to correlate the two, we can have the hidden layer to link the two. And use some weight functions to generate the likelihood of landslide occurrence and check the successful rate of the prediction, and in interior and like a looping process, back and forth to modify the error of the prediction. And random forest is one of the robust non-parametric machine learning approaches. It trains data randomly with a sample with replacement, generating a small subset of data feed as training data to multiple decision trees, like this. You can have multiple decision trees, and eventually you are going to combine all the different decision trees by counting a majority vote from all the decision trees to not overfit the training data. Let's look at the model result and see the differences between those models. And you can see from in this case, using the data from northern Vietnam, and we have the mapping results of frequency ratio, logistic regression, and artificial neural network, and the random forest. And by looking at the color, you will see the frequency ratio is very different from the other three. Also, we can check the histogram, which is the probability of landslide occurrence. Then you can see the frequency ratio concentrate more, have more landslide probability concentrate at around 0.5. And for other models, they tend to predict landslide probability with low value. So in this study, we understand that the index space, the frequency ratio, behaves very different from the other three models. And however, if we want to compare the performance of the four models, we can look at the two figures listed here. And this is these two figures, the relative frequency of the 5 susceptibility labels, showing very low, medium, high, and very high. And for very low, we consider probability, landslide probability is 0 to 0.2, low is 0.2 to 0.4, and median is 0.4 to 0.6, high is 0.6 to 0.9, and very high is greater than 0.9. Okay, and we can see the predicted distribution among the four models. Firstly, this figure is collected from the landslide samples, and this is from non-landslide samples. So you can see that random forest predict more higher probability over landslide samples, which fits the expectation that we want. Compared to other models, random forest significantly outperforms than other models, not only for landslide samples, but also for non-landslide samples. You can see random forest predicted lower probability for non-landslide sample, also fit our expectation. And again, if you check the frequency ratio model, I concentrate at the center label, which means that it predicts more whether it's landslide sample or non-landslide sample over the 0.4 to 0.6. And about the model comparison, and for this study case, we can conclude that the model results is that random forest outperforms other models, and frequency ratio is very concentrated in distinguished landslide areas and non-landslide areas. And however, some issues we have to keep in mind. The quality of input data, for example, the landslide and non-landslide samples derived from the landslide inventory, will significantly affect the model result. The quality of landslide inventory can be questionable because the landslide inventory can be prepared by image processing technique using satellite imagery, or we can use manual interpretation. However, is the accuracy of the mapped landslide inventory is good enough? It's always questionable. And about the model performance, although in this study case we understand the random forest outperforms other models, however, it could be case by case. And when we talk about the accuracy, we have to think about the model accuracy. can use for the model applicability, meaning we are not sure that if we want to use a very accurate model to be a model used for like landslide hazard assessment, and probably it's not, because for example, the random forest model in this study case is gives very certain answers saying where is landslide and where is non-landslide areas, and giving no like uncertainties or buffers for decision makers. So as when the reliability is can be not sure 100%, then this kind of certain model results may lead the decision maker in difficulty in determining if you want to accept this kind of certain answer. It's like yes or no. There's just no buffer. So for that case, maybe frequency ratio or other models like logistic regressions, which can give more buffer or more space for decision maker to understand the likelihood or the probability measured of the landslide occurrence would be much useful. And since a different model generates different results, is there any possibility to combine all the available models? This study issue is very possible and has good potential because if you review the current study, landslide study, you probably will find some researchers has focusing on this issue, combining different models to seek optimal approaches for a landslide susceptibility analysis. And however, nowadays we don't have a certain series for this kind of combination. So probably, in my opinion, it's a kind of good direction for landslide model researchers. Okay, let's move to the session 4, which is an integration method for modeling landslide and debris flow. And I mentioned previously, I would like to take like a 10 minutes break before I start the session 4. Before that, please look at the in-class quiz. And the first one for assessing the slope susceptibility, we know that the slope is more stable when the subsurface water pressure is higher. Yes or no? And the question number 2, models used for landslide susceptibility analysis include statistical models, physical-based models, machine learning algorithms, and all above. Please provide your answer to the assistant. And then I would like to take a 10 minutes break. And so please come back at the 5:20. Is that okay for everyone? Okay, and let's see you later. I will leave for a while. Okay, and then I will focus on a study case talking about an integration model for predicting rainfall-induced landslides, which is a very early publication in 2009. But I think this is a very good example exploring possibility to combine different types of model. So the model series that the model integrates a probabilistic and deterministic approach. It combines a physically based model and a statistical model for assessing landslide occurrence, probability and landslide occurrence. And here introduce 2 new variables, rain intensity differences, RID, in this model. What does that mean? The RID is the rainfall intensity, which is the actual rainfall intensity minus critical rainfall, calculated using the critical rainfall model. So for this integrated model, we have the assumption listing here. For deterministic approach, slope values when RID is greater than 0. If you remember the example that I show you for the critical rainfall model, when the actual or estimate rainfall intensity is greater than the critical rainfall threshold, then we consider it's unstable. So in this case, RID is the differences or the minus rainfall intensity minus critical rainfall. So when RID is greater than 0, then we consider it's unstable. So it's deterministic approach. It says the results by saying yes or no, or unstable or stable. However, in this integrated approach, it uses two variables, RID and D. D is a rainfall duration, which is additionally incorporated in this model. Because from our previous study, we consider the rainfall duration is also important to assess the landslide occurrence. So in this case, landslides will be more likely to occur. We're going to say that landslide will be more likely to occur when the RID is greater, which means it's positive, or the value is higher, plus the D is longer. So we are not going to say yes or no. We are going to say the terms in terms of the more likely to occur. So it's kind of a probabilistic measure. And specifically, we use this method. You can see. So this is the equation of critical rainfall model that I haven't shown you previously. And then we incorporate the critical rainfall model in a logistic regression. And in the logistic regression, we only incorporate two variables. Firstly is RID, which is rainfall intensity minus critical rainfall. And the other variable is duration. So by doing so, we are using logistic regressions, but meanwhile, we also incorporate the critical rainfall measures in this logistic regression analysis. So by incorporating the RID and D in the statistical model, physically, so values occur when RID equals is greater than 0. And however, probabilistically, slope values more likely occur when RID is higher. So the measure of the landslide occurrence is different from yes or no to it's more likely to occur or not. Specifically, if you want to practice this model, you need to calculate the rainfall intensity using rainfall variables, rainfall estimation from rain stations or the QP sum product. Then after you have the actual or estimate rainfall, and then you can use this minus the calculated critical rainfall, and then you can obtain RID maps as here. And by incorporating a duration and RID in the logistic regression model, then you can have this probabilistic measure of landslides. So it's not all like a yes or no, it gives you the probability of landslide occurrence. This is so-called integrated approach. And we also compare this integrated model with the traditional critical rainfall model. And we compare the model by using the landslide data in the Typhoon Taitung in 2005. And this is study area, which is a Baishi watershed in the north part of Taiwan. And the assessed landslide number is 259. And we can see that for integrated model, we predict landslide among the 259. There are 226 landslide can be successfully predicted. And among these 226 landslides, only 172 predicted by critical rainfall model, and 45 landslides are not predicted. And for integrated model, and we still have some landslides that we cannot successfully predict it. And there are 33. Among the 33, none of them can be predicted by a critical rainfall model. And all the unpredicted, and also unpredicted landslides by critical rainfall model is still 33, meaning integrated model is significantly outperforms a critical rainfall model. If we assess the prediction successful rate, it's like integrated model has 87% successful rate, and for critical rainfall model it decreased to 66. So in these model applications, by combining statistical model and a physically based model, we can improve the predicting accuracy than the traditional model. And however, there's still some discrepancy between landslide modeling and landslide hazards. And landslide model is a tool or technique, in my opinion, to evaluate the occurrence of slope value, or an approach to test our working hypothesis about landslides. And however, landslide hazard is the probability of occurrence in a specific period and within a given area of a potentially damaged landslides of a given magnitude. I have listed this definition in previous slide. So in here, I would like to focus on these terms, the potentially damaged landslides, and what are they? We can explore this issue by looking at this satellite data. This is the satellite data taken before and after a Typhoon Molak in August 2009. The location is in southern Taiwan. So you can clearly identify the landslide area over the mountainous slopes. And here, and after the typhoon. And however, if we look at the landslide in detail, in more detail, you will see not only landslides occurred over those hill slopes, but also the companion debris flow or landslide runout movement, landslide and debris flow moved down to the flood area, the floodplain areas like settlements or villages. And you can see some affected areas occupy the settlements and the villages. And the area those people who live in are the main focus of landslide hazards. So here is the scene. If we can have a very good landslide model, we probably can only predict the landslides over here, but we have no idea about the following of the sequence of the landslide, which is landslide runout or landslide or debris flow, how they affect the downslope area and how they damage the settlements and villages. So to build up this kind of framework, we have to identify or separate the characteristic of the entire landslide process. We separate the landslide and process into landslide and the landslide runout. And the landslide runout is the debris flow itself is if it carries amount of water. So in this figure, you can identify that this is the initiation part of landslide. In this study, we call it landslide itself. However, the movement or the path of the landslide failure materials, we call it runout or debris flow. So we have the idea we want to not only perform the prediction of the landslide initiation, but also to assess the possible falling materials and their paths and the positions after landslide occurrence. And for the second part, to understand the movement of debris flow, we use this algorithm. To calculate or to simulate the movement of the landslide rock or debris flow. The overall idea is coming from this two-dimensional flow flux estimation, and we assume that that is a very strong assumption. We assume that debris flux can move and followed by this velocity profile. Okay, in the upper part of debris flow, you can have higher or faster velocity, but in the bottom part, because of the frictions, you have lower velocity. And this by having this velocity profile, you can generalize the flux estimation like this. You just do integrations along these directions. And based on the mass balance equations, you can actually simulate the movement of those flux material. And this is the algorithm that we are using for simulating the movement of debris flow. And let's see an example. This is the debris flow induced by a Typhoon Moloch in 2009. You can identify this is the initiation of the landslide, and those are falling materials then move down to the flooded area and bury some houses here. And not only this one, but also here you have another landslide. In this case, the photo has been covered by a cloud, so you cannot see it clearly. Okay, and based on the all the data we can collect into the, for example, for performing the integrated model and the topographic data for simulating the landslide and debris flow, we can have this simulation result. And this is a dynamic simulation to understand how falling material can move downslope and how it displays and what's the distribution of it and the deposit of those falling materials. Eventually, we can compare the model results with the observations, which is the interpretation using area photo. So we can see over the deposition part, you can see there's still some significant differences between the simulation and the observation. If you look at if we want to dig in the reason, we analyze that. We know that because of the resolution of DEN, and here you can see because of the houses, it stops the movement of the debris flow, and the debris flow can only then move to those major roads. But for this digital elevation model cannot represent the kind of detail. Therefore, that's why we have the discrepancy between the observation and simulation. And however, for some important information can be also reviewed. If we look at the road paths along the mountainous area, we can also identify some road across the landslide scars. For those sections, we can have very good prediction for preventing the disasters over those sections. Okay, this is the overall idea to integrate the landslide model, including the statistical model and the integrated model, and also the debris flow simulation. So we want to build up a modeling framework based on this integrated model. So the overall idea is that For assessing the typhoon-induced or rainfall-induced landslide hazards, we not only need a landslide model, but also we need a landslide runout simulation. And this two parts is used to assess the value initiation. And the second part, the debris flow simulation is used to assess landslide runout and also to evaluate affected area by landslide. Therefore, we can evaluate the landslide hazards. And however, we have more ambitious. How about not only the landslide prediction can be conducted, but also the rainfall brought by typhoon can be also predicted as well. If we can do so, then we can use this kind of modern framework to forecast a typhoon-induced landslide. And here is the study example. And for typhoon forecast, we used Typex, which is a product to forecast the rainfall, the precipitation brought by typhoon. And it incorporates the weather research and forecasting model, and also the National Center for Atmospheric Research mesoscale model MN5, and use different scale. The resolutions for the modern performance, including the East Asia for 15-kilometer grid and the 5-kilometer grid for Taiwan. And to apply this kind of Typex operation, it actually ensemble 18 different predictions. So it's kind of 18 ensemble numbers with setting 18 different initial conditions. Therefore, you can, based on one operations or simulations, you can have 18 different simulation results. And for the typhoon cast, it provides the typhoon tracks and also hourly rainfalls. This is the main product that we need. And 4 times a day, it initiates the forecast 4 times a day. And this is the initialized timing, 0, 6, 12, 18 UTC time at the Taiwan Typhoon and Flood Research Institute. Okay, and then we're going to apply this modern framework to watershed in southern Taiwan, which is the Gaoping watershed. You can see the area is quite big and large. And the Gaoping watershed is 2,800 kilometers square area located here, and the elevation range is quite considerable, from 25 meters to almost 4,000 meters. And 90% of annual precipitation is around 2,800 millimeters falls in the wet season, which is from May to September. And to perform this modern framework, rainfall data and landslide data from 9 landslide producing typhoons were collected. And all these 9 typhoons are all very different based on their track, and also based on the amount of rainfall, and based on their duration, and based on their amount of landslide triggered. Okay, this is the parameters that we use to calculate the critical rainfall. And we use, in this study area, we have 20 lithological units and 24 rain stations. And by considering the differences of the lithological unit, we use different physical parameters of those soil physics parameters, including the soil bulk density, the cohesion, interface angle, and conductivity. And then for rainfall data, Based on the 24 link stations, we use ordinary region to perform the spatial interpolation to obtain the rainfall data for the 9 typhoon events. And as mentioned, the characteristic of the rainfall variables are very different from the very few amount of cumulative rainfall to very high, like almost 3,000 from like, and also we use satellite data, including spot 4 and 2, and Formoset 2 to manually map the landslide for every typhoon events. So now we have the landslide inventory and soil fixed data for critical rainfall model, and the rainfall input to calculate rainfall intensity differences and the duration, and therefore we can generate landslide probability using those parameters. Let's see the result and discussion. Okay, the model performance divided into 2 parts. The first part is about the model development, meaning we use the data from 2001 to 2008 to develop the model. Then we use 2009 Typhoon Morak to test the model. And here, this is about how we operate the landslide forecast. And in the beginning, the TypeX will generate the rainfall forecast every 6 hours. And we assume that after 1 hour, we can finish the landslide modeling and use another 30 minutes to perform the landslide forecast map, and another minute to perform the landslide warming, meaning we are going to announce the landslide where a landslide may occur. So from the release of the rainfall forecast to the first warning is about 8 hours. And after the first 8 hours, every 6 hours, we can produce the warning. And based on the data we collect from 2001 to 2008, we can generate the model and also use the landslide inventory to assess the performance of the model. And we use modified success rate to calculate this, to assess the model performance. The modified success rate stands for MSR equals 0.5 times the successful rate of landslide prediction, and 0.5 for non-landslide area prediction. So you can see these predictions has been divided into 2 parts: the prediction rate of the landslide and prediction rate of the non-landslide. So the first part is about the proportion of landslide number correctly predicted, and the other part is the proportion of the overlap between predict and interpreted non-landslide area. So you can see this is overall accuracy for the previous 8 events. In general, we have 0.78 successful rate, and for a modified success rate, we have 0.78, and from both sides, it's all above 0.7. So it's kind of very balanced model. And we understand from the historical data, it has the capability to produce the successful rate over 0.7. And however, if we use the forecast rainfall data instead of the actual rainfall data, how it can react. And this is the example This is the generated hourly rainfall from the TypeX product. And because this product is hourly rainfall, then we can generate the 24-hour rainfall intensity and the rainfall durations to perform the integrated landslide model. And the entire procedure is that and we have the TypeX raw data, and after data processing, we have the rainfall input, including the 24-hour rainfall intensity and duration. Then we are going to use the two variables and also the critical rainfall data and to the LiDAR model, which is the integrated model that I introduced previously. And because the TypeX products is an ensemble estimation containing 18 different estimations of the rainfall, therefore we are going to have all 18 different landslide predictions. For every landslide forecast, we just average those 18 landslide predictions. So you can count the landslides occurrence 0 and 1 based on the results here. Then we assume that the unstable area should have the probability of landslide greater or equal than 0.5. So this is the prediction results. I would like to use this cartoon to let you understand this procedure easier. Also, you can see we have three predict landslide timing and predict landslide area in percent and warning timing. So, and at this moment, okay, let's know that the actual warning timing is between the August 7th of August 2 o'clock in the afternoon and the 7th of August at 8 o'clock in the afternoon. This is the predict landslide timing. And from here, from the beginning, which is the 5th of August, which is about 2 days ahead of the landslide, we didn't predict any landslide. And then after 6 hours, we don't have any landslide predicted. And also, and then to this is the 8 o'clock in the afternoon in the 5th of August, we predict some landslides, and we predict landslide timing is around the between the 6th, which is 7 o'clock in the afternoon, in the evening, and the 8th of August in the morning, which is 3 o'clock. Okay, and from here, you know, it's kind of this prediction time is kind of wide. However, it include the actual landslide timing, and then we can continue our warning, and like at the morning 2 o'clock on the 6th of August, we predict the landslide timing within this time period. And let's move on and move on. So we can see, we can use the following table to summarize our prediction. This is a warning time. This is a successful rate. And here we also calculate the time before the typhoon arrival. And we can see that when the typhoon is approaching, the arrival time of Typhoon Moraca is at which is the 12 o'clock at the 7th of August, which is here. When the typhoon is approaching, the MSR value it also increases from 0.45 to 0.626, which is not very good. However, if we look at these, we pick up this prediction data from this warning time, then we can find that if we look at the predict landslide size, we will see the prediction capability in more detail. You see, please check that for landslide area greater than 3 hectares, we have higher predict accuracy. You can see when the landslide is very small, the model cannot predict the landslide correctly. However, if the landslide is greater than 3 hectares, then we can have better prediction accuracy. So for landslide with size larger than 3 hectares, we can correctly predict them. And in overall, the MSR can be higher than 0.7. So the application of this modeling framework is like, now we are not able to predict landslide if they are small. However, sometimes they occupy the majority of the landslide number. But when the landslide area or the landslide size is greater, we have better capability to predict them. So for this study case, we have those conclusions. The Typhoon Moraca was selected to practice the landslide forecast. Both reliable landslide model and typhoon forecast are needed to predict typhoon-triggered landslides. And this study has following findings. Firstly, the forecast has better performance in predicting landslide size, predicting larger size landslide, which is greater than 3 hectares. More accurate landslide forecast can be generated when the typhoon was much approached. In this case, the effective warning time is about 40 hours in advance of the arrival of Typhoon Moraca. And by incorporating the integrated model and the TypeX, which is the rainfall forecast data, we can provide useful landslide forecast information for Taiwan. Okay, then let's quickly move to the session 5, which is about a challenge and future work. And I will not place a specific comment for the challenge and future work on landslide study, but I list some unnecessary problematic issue for you to think. And I divided this challenge of future work and challenge things into 3 parts. The first part is about the model practice. And the second part is about the model assumption. And the third part is about model application. And firstly, for the challenge and future work for model practice, we need to ask those questions. How reliable the spatial models are? And how do we obtain independent information to validate our models? Is there any new information available to improve the forecast? How do we combine multiple spatial forecasts? And for model assumption, and how environmental and climate changes will affect the geographical distribution of future landslides. Will landslides occur in the future under the same circumstances and because of the same factors that produced them in the past? So simply, the question is to ask if the past is the key to the future, if the empirical experiences can be valid in the future. And for model application, and how do we define better methods and measures to assess landslide damage? How can we obtain information on the consequences of landslides? Will changes in the frequency and magnitude of triggering affect the vulnerability that we haven't talked about in the lectures? Vulnerability is about how if the society can have a certain level of resistance to landslide hazards. Even for an area, the landslide hazards occurred, but some areas probably have a strong resistance to landslide hazards. Therefore, their landslide risk is lower. But for some area, if they have lower resistance to landslide hazard, the landslide risk of the area will be higher. Meaning, is there any approach that we can adapt landslide hazard? And in my opinion, for landslide study, we need to firstly, we have made a significant progress. We already made significant progress in forecasting where landslide occurred. However, we are not good with temporal prediction of landslide, meaning we haven't do any good prediction in landslide timing yet. We know little about the vulnerability to landslides, and we must improve our ability to transfer results to the end users. This is all my comments for the challenge and future work for landslide studies. And because of the time, I think we have to end today's lectures by now. If you have any questions, please address your question, comments, or suggestions to the TA, and I will review all the comments. If possible, I will give my feedbacks in the future. Thank you.
Thank you, Professor Jiang. And anybody have any question? Oh, Chih-Hung.
Okay, so can you hear me okay, Professor?
Yes.
Okay, so good evening, Professor. So I have 2 questions here. So we know most Taiwan mountain is coated by Chih.
Can you speak louder?
What? Can you hear me okay?
Yeah, please.
Okay. So good evening, Professor. So my question is because we know most Taiwan mountain is coated by Chih. And the tree, it has a roots. The roots, they can be fixed to the soil and the rock. So is your model have to put the effect of the tree to inside, because the tree might be can effect for a landslide, maybe can stable the mountains, the geologist quality. So this is the first question.
Yes.
Yes, what is the first question?
Okay, I can reply now, right? And for the not including my math approaches and my studies, but other studies, they consider to use NDVI as a proxy to correlate the loose strings. So there are some empirical equations to correlate the loose strings and NDVI, meaning you can apply NDVI to estimate loose strings and apply it to the model. And however, we still have very valid experimental evidence showing this kind of reliability of this correlation between the 2 factors. So from now, they are all empirical. So your question is a good one. This is very important directions to understand how the root to affect the slope resistance. We need a quantitative methods to measure it, but we haven't have that yet.
Okay, so my second question is that we know Taiwan has something mountain. This is a fracture zone. So this part of the mountain has partially to appear landslide, but other part of the mountain, maybe their rock, this is a very complex, so this is not easy to appear landslide. So have you put this kind of geography difference into your model? Because I see they can make your model accuracy is the highest.
In my personal studies, yes, I did. The overall idea is quite straightforward and simplified. You can consider a multi-layer structures in your model framework. Like you can incorporate soil and then fracture rocks, and the rock fracture level can be different in different layers. But by doing so, you need a clear local investigation. You need the field data, even the borehole data to support the modeling parameters. So it's very to apply this kind of model. It's very difficult to to use for wide range area. Maybe just can only apply for local slope that you can really show the fractal structure.
Okay.
So this is a very challenging one. Yes.
Okay, thank you, Professor.
Anyone? Oh, P-Joe. P-Joe, can you hear me?
Yes.
Hey, what's your question? Please unmute by yourself. If you have any question, you can write down in this Google form, and we will send the result to Professor Jiang.
Okay. Why an earthquake will make a differences in on the slide model? I mean, in the landslide model, right? Nowadays, we have seen many researchers consider earthquake as a tracking factors in statistical model or empirical model. But for fixed point based model, they are very few, because again, if you want to build a fixed point model, you have to know the details of the slope structures, including the joint and the fractures and water table, all the parameters, which is very difficult to obtain. Some laboratory experiments has built up this kind of model, but few models have been applied for wide range area, for example, for entire catchment. But for a specific slope test, you still can find some articles talking about that. But if you are saying what an earthquake will make a differences in a slide model, I just can say that if you are talking the differences between different trigger mechanisms like the water and the earthquake, I would say for earthquake slope stability analysis, you have to consider the energy produced by the earthquake will be the major things, and how a slope responds that energy. So it's very different modern framework between the rainfall-induced model.
Okay, thank you, Professor Jiang. Thank you very much. I think it's time, and please everybody write down your answer for last two questions in Google Form.
Hello, can you hear me, Professor?
Yes.
Sorry, I forgot to ask you one question. Is that we know there has another type of landslide system called creeping. So I mean the mountains inside the soil and the rock they use very slowly speed to continuously move down. And then when over the 1 minute, suddenly they become a big landslide. So what's the effect of the creeping in your modeling set for landslide prediction?
Okay, for creeping, because it's not a rapid movement, and for creeping is like, as you mentioned, it's like a slowly and gradual movement of the landslide, and normally happened in the relatively gentle slope. But because the movement mechanics is very different from landslide, so I didn't directly use the creeping concept in the landslide analysis. However, the creeping creeping process can affect the soil depths, and which is also a very important parameters in the landslide modeling. And how creeping will affect the soil depths, you can see an article, I forget the name, published in Nature in 1997. I don't remember the name of our author. But if you use creeping and the soil depth as a keyword, and you can find out an article published in Nature describing how the creeping to form the slope shape in a geological time scale. And therefore, we can, because the creeping is like a flux over the slope, it has the in and out. So it deals with the mass balance. So you can use this characteristic to estimate the soil depth for long term.
But maybe the landslides is a generation from creeping before landslide already happened.
It's very likely. And I got your question. So for a larger landslide, especially a landslide greater than 10 hectares, and in the definition in our geological survey center, they consider before a large landslide occurred, the creeping process can be observed in advance. And some techniques has been applied to monitor the creeping process, like the local GPS monitoring, and use the INSAR technique to understand the deformation of the surface. They are the prime. I agree what you said. The priori Hillside process before landslide. That's very likely. But the critical thing is not. You can find the creeping process almost everywhere if you go to mountainous area. You can easily identify the creeping process by look at the bend of the tree stem. But some areas are relatively stable, although the creeping process isn't going on. But some areas you can find out the creeping process exists, and in fact, actually, those areas are indeed dangerous, and has high chance to have landslides. But nowadays, I haven't seen any researchers talking about it to correlate the creeping and landslides. Although I can agree that the creeping can be an indicator of the landslides in the future, but doesn't mean that the other creeping areas can have landslide in the future.
Okay, thank you, Professor.
In lecture, you showed the differences in prediction success rate of two methods. Where were the model prediction made before or after the actual event? I cannot really get what you're going to ask. Okay, if we are saying the study case that I have is we use historical data to develop model, and we have to evaluate the model performance based on historical data as well. If we check the model performance using historical data and the model success rate telling us it's okay, showing like the accuracy is higher than 0.7, then we can somehow use the model for future prediction. Like in my case study, I use the model developed using the data from 2001 to 2008. Then after the model can have been developed, then I use the model to predict the landslide in 2009. So, and the prediction rate, as I mentioned in my lecture, the prediction rate is not quite well incorporating the rainfall forecast. The accuracy is just achieved to like 0.66. And however, if you look at the detail of the model prediction, with considering the different size of landslides, it says if we focus on the prediction of the larger landslide, which is greater than 3 hectares, it can achieve the prediction accuracy over 0.7.
Okay, seeing no more questions. Thank you, Professor Jiang. Thank you.
Okay, thank you. I believe it's time is quite. I think it's pretty much for today's lectures, and everybody is hungry as well as, and I have to do my work cooking for my wife. So if you have any questions, please use the link to address your questions, and I will see them and give my feedbacks. Thank you.
Thank you, Professor Jiang. Bye bye.
Okay, bye bye everyone.